OCR A-Level Chemistry, Module 6, Part 2. This goes from extending the carbon chain all the way up to the end of NMR, and that is all of the A-Level content for this course done. So let's get right down to it. You can extend the carbon chain by forming extra carbon-to-carbon bonds, and you can do this through adding nitrile groups. So when you have a haloalkane, you can react it with a nitrile group that's dissolved in ethanol, and you'll end up with an extended carbon chain. And we do this with a mechanism. This is nucleophilic substitution. Make sure you know this for your exam. And this is how you extend the carbon chain on a carbonyl group, and this is nucleophilic addition. Only in this one, obviously, you form an intermediate that then reacts with water to create your alcohol with an extended carbon chain. These nitriles can be reduced or hydrolyzed with nickel and hydrogen to form amines. Reacting a nitrile with water and hydrochloric acid gives you a carboxylic acid and ammonium chloride. Now for benzene, it's much easier. You just add a hydrocarbon if it's an alkyl group that you want to add in the presence of a halogen carrier, and we went over that last time. For creating aromatic carbonyls, it's almost exactly the same. The next big bit is practical techniques, and the first bit is about quick fit apparatus, and this is in my Module 4 video. I don't particularly want to go over it again, so definitely go check out Module 4 if you haven't already. A new practical technique is filtration under reduced pressure, and you use this to separate solids from solvents. You do this with a Buchner flask and funnel and filter paper, which I have helpfully drawn on the next slide. So you add your solution in the top, and it filters into the flask. Under reduced pressure, it just means it happens faster than it would if you just did normal filter paper. Another practical technique is recrystallization, and you use this to purify solids. So you heat your solvent, could be ethanol, could be water, and you slowly add it to the crystals until they dissolve, and we call that the minimum amount of hot solvent. Once everything's dissolved, you cool it, and then you filter it under reduced pressure again, and you should get a pure product. You can check the purity of your products using the melting point. A pure product will have a sharp melting point. An impure product will have a broader one, and it will probably have a lower melting point as well. Make sure your sample is 100% dry and free-flowing. Then you're going to take a glass capillary tube, which is like a thin, hollow bit of glass. You're going to rotate it in a Bunsen burner to seal one end of it. Then you let it cool, and you fill it with crystals, about 3 millimeters deep. And you do this by dipping it in the sample, and then you gently tap the sides of it until it falls to the sealed end. And then you find the melting point, and this is how you find the melting point. So this is a melting point apparatus, and before you start using it, you're going to want to know roughly what temperature you're looking for. So you put your sample into the apparatus, you look at the thermometer, you turn the dial all the way up so you're on rapid heating mode, and then when you get close to your melting point, you're going to turn the heat way down, and you're going to look through the viewing port. And then when the sample starts pulling away from the sides of your container, you're going to note the temperature, and you're going to keep noting the temperature until it is completely melted. Also on the spec, you need to be able to identify functional groups, predict the properties and reactions to form certain products, and the routes to get to said products from given chemicals. Now we need to learn about chromatography, and there are different kinds, but basic chromatography is working out the RF value, or retainment factor, and that's the distance moved by the component over the distance moved by the solvent. You can then measure this retainment factor against the known value for the compound you're doing. This only applies to TLC and paper chromatography. You can also carry out gas chromatography, which looks like this, and would you believe it, it's called a gas chromatogram. So your inert gas from your flow valve acts as your mobile phase. Components are absorbed into the stationary liquid phase, and more soluble components are slower. And so this means that they have a longer retention times. They reach the detector later than others. You can find the concentration of each of these with the area under the peaks that come in your recorder, and that's one advantage of it over paper or TLC. So to find the concentration, you're going to use a standard solution, something you already know the concentration of. You're going to obtain the gas chromatograms for all of them, and then you're going to plot a calibration curve of peak area against concentration. Then you obtain a gas chromatogram of the compound you want to find, and then from that you compare it to the calibration curve and you can find the concentration of that compound. You need to know your qualitative analysis tests. So carbon-to-carbon double bond, obviously bromine water decolorizes from orange to colorless. Haloalkanes, you can use silver nitrate and it forms a colored precipitate. Phenol is acidic, but it doesn't react with sodium carbonate because it's not that acidic. Carbonyl groups, you use 2,4-DMPH and it goes from an orange solution to an orange precipitate, and then you can use toluenes to identify aldehydes. And it will form a silver mirror at 50 degrees Celsius if an aldehyde is present. Primary and secondary alcohols can be oxidized with an oxidizing agent, acidified dichromate, or in this case potassium dichromate, and that would turn from orange to green in the presence of an alcohol. And reacting carboxylic acids with sodium carbonate forms CO2, which you can test for obviously with lime water, which will turn cloudy. Now finally we're doing NMR, and we're starting with carbon-13. So you use NMR to find the number of different environments in a molecule. And by the way, 0 is not part of the different environments. 0 is what we call TMS, or tetramethylsilicane. And we use this as a standard because it only has one environment. The x-axis is parts per million, and it starts on the right-hand side at 0 and works left. So you can see here that there are 4 different environments because there are 4 different peaks, not including the TMS peak, because like I said, it's a standard. So the first way to check environments is to look at what each carbon is bonded to. So in this one here, there is one environment because each carbon is bonded to 1 carbon and 3 hydrogens. Whereas in this, there are 3 environments because no carbons are bonded to the same number of hydrogens. So the spec says that you need to be able to determine how many environments a molecule should have. So let me walk you through this example. So the 2 carbons that are double bonded to another aren't in the same environment because one is bonded to a methyl group and the other is bonded to an ethyl group. Both CH3 groups are different distances away from the double bond. So this molecule isn't symmetrical, so all of the carbons have slightly different environments. Now, where the environments will show up on your x-axis is in your datasheet. So make sure when you have a question on NMR, you look at the datasheet and make sure you look at the carbon-13 and not the proton NMR, because that's next. So, if you number the environments in our molecule, starting with the functional group, outwards, you end up with an NMR that looks something like this. I've written the range of the 2 environments in the top right-hand corner. The carbon peak that we assign to the second carbon is closer to the C to C region because it has more C to Cs close to it. And likewise, because carbon-3 is more influenced by the carbon-to-carbon double bond, we put it slightly further up in the carbon-to-carbon region. So moving on to proton NMR, like the name suggests, this is with hydrogen. So in propane, which is the example here, there are 2 environments, and hopefully you can tell why. because the environments on the two CH3 molecules are the same, and then there's a second one on the CH2. So because there's two of the CH3 and one of the CH2 environments, they will show up in a ratio of 2 to 1, because unlike carbon NMR, proton NMR can show the ratio of environments. And you can find this ratio with peak areas, ratios, or through integration. And exactly like carbon-13 NMR, you can find the environments by looking at the molecule's displayed formula. So in this one, there are 4 different environments, again due to the different proximities to the OH group. And again, the peaks you would find for this are in your datasheet. And again, there will be a peak at 0 for tetramethylsilicane. And then comes something called spin-spin coupling, and this is when a proton spin interacts with protons around it, and it helps you know how many protons are bonded to adjacent carbons. So you split your main peak into different subpeaks, and the number of subpeaks determines how many adjacent protons there are. The number of adjacent protons is equal to the number of subpeaks plus 1. And this is an example. So 1 peak means no adjacent hydrogens, 2 peaks means 1, 3 peaks means 2, 4 peaks means 3, etc., etc. In a molecule such as this, the hydrogens split between the two groups, and it forms something called a multiplet, or a multiplat, I'm not entirely sure. So spin-spin coupling always occurs in pairs. So there'll always be a pair of splitting patterns when you're looking at NMR. Now, if you look at your data booklet, you'll notice a serious problem, and that is that the OH and NH group go all the way along the x-axis. So you run proton NMR, then you add heavy water, which contains deuterium, which is an isotope of hydrogen that has 1 proton and 1 neutron, so an atomic mass of 2. And what happens is something called a proton exchange, and the OH group becomes an OD group, and deuterium doesn't appear on proton NMR, so the OH peak or NH peak disappears from the spectrum. And because it's deuterium, it doesn't take part in spin-spin coupling, so the peak is quite broad. So that is it for OCR A-level chemistry. I hope you enjoyed, and I hope this helped. If you haven't checked out the other videos, definitely do. I hope you enjoyed. Please remember to like and subscribe, and I will soon start doing some past paper walkthroughs, so look out for that. Thanks for watching. I'll see you around. Bye.